In our last videos we have developed our system of counting, and we have used 5 fundamental axioms to develop that system, and then from those axioms we have proved certain theorems so that our system of counting behaves in the way we want it to behave. And these were those 5 axioms, and we had an example of pebbles. We had pebbles, and we wanted to count them, and by counting we meant that putting those pebbles in one-to-one correspondence with the numbers in such a way that we can account for all of the pebbles in such a way, and hence we developed a system and we called it 1, 2, 3 and so on until the nth number. And abstractly we developed it x, and then to the successor of x, and so forth. Now we have developed this system and it counts, it behaves as we want it to be, but this is a very limited system. Of course we would like to do other things with our system of counting as well. So in this video we will develop an operation that we will call addition, and all of you, I assume that all of you who are watching this video must have some idea what addition actually is. This is the first thing that we learned at school. After learning to count on fingers, this is the first thing we learn. But so far the tenet of the course has been to assume that you know nothing, and you have actually forgotten everything you have learned at school. And so we'll define addition in such a way, and then we'll prove it. Another thing that I would like you to bear in mind is that addition, no matter how fundamental an operation it is, we will be developing it using these set of axioms, and we will not be developing it as an axiom. We will not take it for granted. We will actually derive it from these axioms. This is going to be a tedious proof, a little difficult at this stage, I would say. This would be divided into 2 parts, but then I will try my best to explain it as easily as possible. So without a further ado, let's delve into it. So this is a theorem that we will be proving. We'll call it a theorem 4, and this will also be a definition, the definition of addition. And what we are going to prove is that for to every x and y we may assign a natural number x plus y. This would be a number in a unique way. Now this is important. There's only one way this could be defined, such that it satisfies the following properties. The property 1, that x plus 1 is equals to the successor of x, or x prime as we'll call it, for all x's. And the property 2 is that x plus y prime is equals to x plus y whole prime for all x's and for all y's. Now we will do it in 2 stages. First we will develop uniqueness of it. By uniqueness we'll prove that there's only one way this can be defined. There's only one way this number could exist. There's only one number, x plus y. And the second part would be to prove the existence of it. In this part we'll show that this actually exists, that this type of number that satisfies these 2 properties actually exist, and we'll derive it from these axioms. So for the first part, what we are going to do is that we will show that for each x there is a unique possibility of defining x plus y for all y in such a way that these 2 properties hold. Now we can write it any other way. X plus y could be written any other way that you would like. You can write it like this, you can write it like this, or you can write it like this, or any other way that you would want it to be. So we'll write it in 2 of these ways, and then we will show that both of these ways are equal to each other, and then we would have proved that these are unique. So first we will define it in such a way. So we will write it like this. For x plus 1 we can write it like this, both of these expressions, and then we can write like this, both of these expressions, x heart 1 or x trefoil 1, whatever you call that. And then we will do an induction on them. And do you recall what induction was? Well, actually we assumed that there was a set. Set was just a bucket for us. We did not formally state what set was, and set was a bucket. You have to assume, well, a part of the proof is also to assume that this is a bucket, and we had to show that 1 is in the set, 1 is in the bucket, and whenever x was in the bucket, so was the successor of x. And if we had proved these two statements, then we had proved that this, whatever statement we were proving, it held for every member of the set. And this is what induction was. So this is what we are going to do. Well, the first part of this induction will be to show that 1 is in the M, and by the definition, by what we have defined x heart and x trefoil y to be, we can say that the first condition holds, and so the first condition holds, and this also holds. And then we can say that x heart y and x trefoil y are equal to each other, and so we have shown that actually 1 is in the set and 1 holds and 1 exists. And the second part is to show that whenever x is in the set, the x prime is also in the set. So we have this condition that x heart y and x trefoil y, this is the way we have defined it. And by what was axiom 2 now? You have to recall what axiom 2. Axiom 2 was that whenever two numbers are equal to each other, their successors were equal to each other, and they were unique successors. So by axiom 2, this holds for the x prime also. It also holds for the successor of x, right? And so we have proved it for y prime, and so this induction was actually on y, all y's, and hence we have proved it for all y. And so by induction, by axiom 5, we have proved it that these two operations are, or these two numbers are unique. And no matter how you define these two numbers, you can have any other pair, and you will always end up with them being equal to each other. So this way you can prove that this is unique. And so we have proved that so we have proved the uniqueness part of it, that whatever that number is, it is unique. And now the difficult part is to show that it exists, this operation, this number exists. So this is the existence part of the proof. And so to prove existence, we have to show that for all x, it is possible to define x plus y for all y in such a way that x plus 1 is equals to x prime, x plus y prime is equals to x plus y whole prime for all y. And we will again use induction to show that this holds. So we have to find a definition that satisfies these conditions for being a member of a set M. And if we can find such a definition that satisfies these conditions for each x, we can say that for all x this definition is possible, and we will hence we would have hence proved the existence. So we will assume that there is a set M, and be that set of all x that satisfy these conditions. Then for x is equal to 1, the first case of induction, right? So for x equals to 1, we have to suppose this. This supposition is actually what we would require for us to satisfy that these two properties hold, and so existence would be proved. And so this is the requirement, this is the required number. And then for the first case, we can say that we can set y is equals to 1, and then this expression would become 1 is equals to 1 prime. And so because this is x is equals to 1, this would actually be x prime. 1 prime will be x prime, because this was the first case, and this is what I'm trying to show here, right? This part. And so this holds. Using this number, this satisfies the first condition. Now we'll have to see whether it satisfies the second condition or not, and to do that we will write it in this way. Now if this is a successor of y here, what would this be? This part be? This part would be successor of y, right? Now again, what is this part actually is? This part actually is the same thing, right? So we can write it like this part. So this should be written like this. So here's the typo here. This should be like this. And so we have proved this also. We have proved it for the second part as well, that 2 also holds. And so 1 is in M. So the first part of induction, part A we can call it, where we have to show that 1 is in M, is now complete, right? And so we have to show this is now the part that is left is part B, where we have to show that whenever x is in M, then x prime is in M2. Now this is the part B of the existence part of the proof. Here we will show that whenever these two properties 1 and 2, whenever they hold for x, they also hold for x prime. So what was the first property? It was in the last part, in the part A, the number that was required was x plus y is equals to y prime. This time this is the number that is required. This is the number, if we'll use, will result in the proof of the existence part. So if we set y equals to 1, from here we can write it like this. And because we know that x holds for 1, from this it follows that we are just expanding this part. So it will follow that this is from here. Hence 1 holds whenever it holds for x. Whenever it holds for x. Hence this property exists. Now let's see if the second property exists also. What was our second property? Our second property was 2x plus y whole prime. So to prove this, what we can do is that we can expand this and set y here. Let's set y to y prime, and we can write this expression as such. Now if we follow closely, we can expand this part. How can we expand this part? We can write it like this. Because this second property, we know that this actually holds for x. It holds for x. But we have to prove that that whenever it holds for x, it also holds for x prime. So we can expand this like this. We can write it as x plus y whole prime following this second rule. Now we would like to further expand this, and we can do this. by writing it like this: x prime plus y prime. Now how have we written that? How have we come to that? We have come to that from this rule, from here, because this part is same as this part and this part, and so we have expanded it using that, and this is what we have written. And this part, and here is the successor of that, because this was successor here. And so we have shown that 2 also holds for x prime whenever it holds for x, and hence we have shown that both of these properties exist. And so we have proved the uniqueness of addition, that x plus y is a unique number, and it exists. So these were the two parts, and it was a tedious proof, it was a difficult proof, but we have seen that how step by step it follows. Now I would like you to appreciate the full proof once. Here is the proof, the uniqueness part of it and the existence part of it. And I would like you to, if you have not understood anything, then I would like you to go through the proof again, and you may ask questions in the comments also, and I would be happy to help. And again, I would like you to appreciate that we have this is nothing new. We have derived it using these 5 axioms, and in our next part, in the next videos, we will be proving some other properties of addition, and then we will also see what is the intuition behind addition, and then we will be building our system of counting, our system of numbers further. So see you in the next video.